talk. And it's a pleasure to introduce the next speaker, Christian Robert, who is on Zoom. Can you hear us?
Yes, I do.
Okay, great. So Professor Christian Robert is a professor of statistics at the University of Dauphine in Paris and the University of Warwick, UK. His work is on Bayesian statistics, computational statistics, and latent variables models. His talk is entitled "Inferring the Number of Components in a Mixture, Dream or Reality." So we'll see if it's a dream or reality. So please, Christian, the floor is yours.
Ok, grazie. Prima mi dispiace davvero di non essere qui. And that's the end of my Italian talk. So I'll introduce my slides. Where are they? All right. So yeah, I'm very sorry not to be with you for reasons I could not escape. And so today I'll try to just give a broad overview of my views on estimating the number of mixture components using Bayesian statistics, which connects very much with Sylvia's previous talk, albeit at probably lower density level. So part of the talk is based on a joint work with several authors, including Judith, who's always in the room right now. So let me try to expand that. Yes. Okay. So this is the outline of the talk, and I'll mix inference questions with computational questions about estimating the number of components. So I'll talk about Gibbs sampling and Bayes factors and different ways of approximating Bayes factors. So I mean, I'll quickly through those slides because again that follows from Sylvia's talk. I'm interested in estimating an object that is a mixture of distributions with a certain number of k of components, and those elements of the mixtures are all well defined. So there is no question about the definition of F1, F2, Fk. They are parameterized with an unknown number of components, or known number of components with and with parameter setters. One important thing is that usually the weights are distinguished from the other components and are differently estimated in terms of ability of estimating them. In the sense that, well, the hierarchical model that comes with mixture is not directly linking the setters and the p's, because the p's are linked with the latent variables. So what are the motivations for using a mixture? Well, usually there are many. Either they are, purely parametric, and this links with Sylvia's talk in the sense that the data is really made of several subpopulations that are merged together for a lot of possible reasons, but the original populations or subpopulations have a meaning. So in that case, inference about the parameters and the populations come together, and that's the point about clustering. Otherwise, there are less parametric goals, like the semi-parametric perspective, or even the non-parametric perspective, where the mixture is just there to replace an unknown distribution. And in that case, maybe the question of estimating of components is less relevant. So somehow I will mostly focus on that part. Well, look, usual quote about mixtures is due to Larry Wasserman, that mixtures are evil. And the reason for that is that, I mean, despite having a manageable likelihood and a very nice narrative that comes with them, I mean, inference is somehow hard when looking at all aspects of the mixture, namely estimating the parameters, the weights, the number of components, and the allocation of the variable, with the later being actually not directly inferable, because, well, it's an entity that comes only once. You only observe it once, and I mean, there is no reason to be consistent on that aspect. Okay, so I mean, one illustration of this difficulty is the identifiability of the parameter. Here is a very simple example where only two parameters are unknown: the mean mu1 and the mean mu2 of the two components. And if you look at the likelihood surface, right, I mean, it's kind of beautiful, but it has two modes. One that corresponds to the truth, essentially, because here I drew a mixture sample, knowing mu1 and mu2 being 0 and 2.5. So this is essentially where the mode is. But there is a second mode that remains from well, kind of atavistic memory of the non-identifiability occurring when p is 0.5. Of course, in this simulation, I use 0.3 and 0.7 as a weight, so there is no lack of identifiability. But by continuity, the deformation of the likelihood coming from this case when p is 0.5 came as the remainder. So that's why I call it atavistic. So when you draw inference on mixture, because you can compute the likelihood, you can compute the posterior, and whatever choice you have on the components and the parameters of those components, you can compute numerically the posterior distribution. That means that simulation is on principle feasible, because there is a numerical value that you can compute fairly quickly. Because if you get back to this picture, I can draw this picture, meaning that I can compute the likelihood for a lot of values of the parameters. So this is not a stopping game. In that case, in sense that this is computable. However, I mean, the real meaning of the mixture, and this is very true for Bayesian inference, is that I mean, the computational difficulty or the real meaning is in associating all the observations into clusters, that is, allocating observations to one of the k components. And then the interpretation becomes k to the n. So this is not feasible. And this translates into the computational difficulty in exploring the posterior, despite the numerical availability of this posterior. And so along the years, I've always found this an interesting challenge, and with no clear outcome on accelerating the exploration of that posterior. And of course, this becomes even more challenging when k is unknown. Because, I mean, in most settings, and I'll come back to that when chatting about label switching, I mean, there are always a lot of modes on the likelihood, and therefore exploring these likelihoods kind of blindly or myopically is a true challenge, because there are gaps between the modes, and therefore any random exploration falls into the gaps. And then, I mean, estimating the parameters one by one, of course, including k, is a challenge due to this multiplicity of modes and a form of weak or strong exchangeability of the components. So in the worst case, all the expectations of the theta i's are equal when you flip around i's, which means that you have to look further for estimator. However, if I plot the density through through replicas of MCMC steps, that provides a direct estimator of the density per se that, of course, ignores some of these difficulties, but fits the data in that example quite nicely. So there is something that is produced by MCMC exploration that standard analysis doesn't return. And of course, estimating of components is part of this difficulty. So as well known and mentioned already, that I mean that the latent variable interpretation is somehow central to the Bayesian analysis of a mixture, even when it is not a quantity of interest, as in semi or non-parametric analysis. But I mean, going through this demarginalization of the original model by introducing the latent variables is both a natural and a feasible approach that returns some items of information from the early days of the Gibbs sampler, on which we work with Jean Dibble at the very early days, and most further usages of this latent variable representation follow from this principle. So the Gibbs sampler remains a nice approach to handling a mixture model, with some caveats like this one, that if you start at the wrong spot, the Gibbs sampler may fail to have enough energy to reach the central mode of the posterior, because, well, in this example I already mentioned, both modes are not at the same height, and well, this is in log scale. This one would disappear in the regular scale. But starting near this mode with a regular Gibbs sampler without doing some kind of tampering steps does get us stuck. Now, another aspect I would like to chat about is the notion of priors in mixture model, because again, that's a bit frustrating and a bit of a challenge, that if we try to push for less informative priors, starting with weakly informative priors a la Gelman, we have either difficulties or a range of options that do not return the same outcome and the same performances computation-wise. And so, I mean, the most natural starting point is to use some form of conjugate pairs, which require specifications of their hyperparameters. And so, I mean, from the early days in the paper with Jean Dibble, and this has been found in a lot of the literature, including the reversible jump paper by Sylvia Richardson and Peter Green, you can use some form of hierarchical base pair where some of the parameters are estimated from the data, but of course that has a possible impact on, a clear impact on the inference. But I mean, the alternative of using improper pairs is prohibited. As such, if replacing these estimators by flat pairs at the higher level, and some of the alternative, again, as Jeffreys pairs, are not directly implementable in that aspect. We'll come back to that later if I manage to go through all my slides. Now, we had tried a sort of trick in the original papers with Jean Dibble that was that all components had to have one allocation. So this was an exclude empty component principle, that in the Gibbs sampler we would always reject allocations where a component would remain empty or with one single allocation. And this changed the model, I mean, considerably, of course, because there was the number of clusters was always a number of components. Nonetheless, a bit later, Larry Wasserman managed to show that this was a consistent restriction in the sense that as n would grow to infinity, we would produce consistent estimations of the various parameters of the model. But, well, it's only for n going to infinity. Now, reparameterizations have been considered in the literature in different papers to try to use uniform priors. So resorting to, well, less informative priors was tried earlier. And I mean, I won't dwell on this slide because actually I want to propose the ultimate reparameterization in a later slide. But there is a possibility to remove this independence assumption in the prior, and in exchange get less informative priors. And the reason for this ban on improbability is linked with my never leave a component alone trick, in that if there is no observation allocated to one of the components, then this is always a possibility. The posterior for that component is the prior. So if the prior is improper, so is the posterior, assuming again independence between the component in this case. Now, estimating k per se has also been considered from the early days. That is a hierarchical model with a prior on the number of components, and if this prior has positive mass everywhere, like say a Poisson prior, you can demonstrate a consistent estimation when using Bayesian inference. And this was shown, for instance, by Agostino Nobile and other papers, including the reference paper by Miller and Harrison in both 14 and 18. Now, in terms of implementation and the impact of the prior on finite n sets, there is a wide range of possibilities, from reversible jump that has pros and cons in terms of implementation, the saturation approach, where you sort of kill the competition by putting a large number of components, favoring sparsity, so large number of allocations to one component and very few to others, and under very regional conditions, you can empty the superfluous components. This was demonstrated by Judith and Kerry in this famous 2011 paper. And then you can run, you can move from estimation to testing and running a Bayesian comparison, say by base factors. If you can implement this comparison on a large number of models, and again, I'll talk about that in a few minutes, then this is an alternative to estimating directly the number of components. And then there is the sort of biased approach using clusters that Sylvia discussed in the previous talk. That is not necessarily eventually consistent, because that's a point made by in this Miller and Harrison reference paper, is that well, number of components and number of clusters turn out to be close as the number of observation increases, but there is still a lingering danger that if you just let the number of clusters grow with n through a Dirichlet process mixture, then it's not necessarily consistent. While if you fix the number of components at the start, then you're facing the difficulty that you're not necessarily estimating the number of components. So I'll skip through the details of using the Dirichlet process mixture. That's a fairly common model where, well, essentially you build a hierarchy of model using a certain prior pi of m on the unique parameter of the Griffiths-Engen-McCloskey model where M is, well, the parameter in the stick breaking representation of the weights in the well, infinite mixture behind the Dirichlet process. And in that case, I mean, you can get availability of the conditional distribution of the data given the latent variables and this parameter M if G naught is chosen nicely in this representation. So I'll come back to that later because that's directly of use in computing the base factor. Now, label switching is both an issue and not an issue, depending on the perspective. I mean, it is there facing us when we implement, for instance, a Gibbs sampler or any representation or computation that depends on the indices of the mixture. But I mean, in a sense, it should be there by the nature, due to the nature of the object we are trying to simulate. So if we observe it, I mean, it should be a nice thing. It just pushes us to look for different form of inference rather than using the posterior expectation as the de facto standards. However, in most situations, we do not observe label switching due to, well, the lack of energy behind or sampler. And so there are tricks to try to avoid, I mean, to increase the energy of the sampler. But I mean, those tricks may prove costly with a large enough number of components or a large enough number of observation. So, I mean, the tricks like imposing constraints are not very recommended, at least from my opinion, because, well, they don't necessarily exhibit enough mixing in the resulting sample. And we're labeling towards one of the modes that, well, I've suggested in some of the earlier papers, including the one with Gilles, is also a costly attitude. So we should instead favor sampling methods that avoid the labeling and therefore work in another dimension, as I will mention in a minute. Just mentioning in passing that in the 2000 JADA paper with Gilles and Merrily, we were advocating this type of approach that avoids the allocation and the indices. For instance, looking at the clusters is invariant to labeling. Now I've reached maybe the central point of the talk about the base factors, and well, the work we run with Adrien Hérault and Judith in the past year. Let me to reconsider the approximation of the base factor. So I mean, the base factor is based on the marginal likelihood that is integrating out all the parameters of the model except the number of components and looking at the posterior probability of that number of components. So I mean, this evidence has computational difficulties because we need to integrate our A parameter space for each model. So there is a multiplied difficulty in this exploration, and there is a huge literature on trying to improve this computation. And not starting, but containing in particular this whole book by Chen Chao and Ibrahim in 2000 that addresses this very difficulty. And why is it of interest? Because there is a minimum validation found in the literature that when you're comparing models based on different components, there is a form of consistency that again, well, starts at least with Agostino Nobile's 94 paper. And even when comparing a finite number of components with an infinite number of components, there are results in the literature, to which we just added. And well, here is an illustration from our paper on comparing a finite mixture with an infinite mixture using a base factor. And well, in both situations, it goes above zero, a lot or a little, depending on the situation. And so, I mean, here is, for instance, a result from our paper that and show that statistically as n grows to infinity, and there is a finite number of components against a Dirichlet-Parry alternative, we do get that means the marginal goes down in the Dirichlet case, and the convergence to the distribution happens at a certain speed of log n to the power q over root n. Now, computationally wise, I find this a very exciting problem, maybe, well, too narrow for certain, but quite exciting nonetheless. Namely that in the range of proposals is huge, and there are interesting challenges to be found in all of them. To start with, there is this huge, long-going debate about Sid Chib's approach to finding a numerically convergent approximation to the evidence, and Sid's approach, which is also called the candidates approach by Julian Bizag independently at about the same time, is that you just take advantage of Bayes' theorem, namely that if the marginal is the join divided by the posterior. So if you want to approximate numerically this quantity, all you need is to approximate numerically that quantity, and the only challenging part is, of course, the posterior that is not available exactly. And so Sid's proposal was to replace this with an approximation. And in the case of mixtures, there is a Rao-Blackwell version of the posterior, which is the average of full conditionals given a sequence of that. And well, I mean, this Rao-Blackwell solution was proposed from the start when the Gibbs sampling algorithm was proposed by Gelfand and Smith in 1990, because this is a parametric approximation to a density, and so it's converging as one of a root t and not with non-parametric rates. However, there is a difficulty that if we are in a mixture model and the Gibbs sampler is not properly converging, in the sense that it is not exploring the k factorial modes that are present on the surface of the posterior, this becomes a very poor approximate to the posterior. And so there is a need for evacuating this difficulty and imposing full exchangeability in the posterior. So this is found in several places in the literature, in particular in this paper by Berkoff et al. That replaces the original Rao-Blackwell with a second average over all permutations. And of course, this is correct, and this avoids the original difficulty with Sid's solution, but on the other hand, it has a k factorial impact on the computation of this approximation. And since we are already averaging over all or most of Gibbs iteration, this induces a considerable increase in the cost. Just to show this impact of relabeling, namely that if you forget, well, this is a famous data set that well, we should not choose according to Redford-Neal, but that provides a benchmark. If we don't use the averaging across permutation, the well, say CHIPS solution returns a log evidence of -105, while if we average across all permutations for k equals 3, which is of course feasible, this moves to a -103. And actually the difference is almost exactly the log factorial 3, which should be there thanks to this number of permutations. So we are exactly using one of the 3 factorial permutation when using CHIPS estimates without the correction. Of course, this degenerates as we increase the number of components, because then the different components or different modes will start overlapping as k increases. So this perfect separation between the mode vanishes with k. So, I mean, this is feasible up to, well, to 8, and with a large number of Gibbs iteration, well, except that for when k increases, we cannot keep all permutations. So, for instance, this paper with Kate Lee and Jean-Michel Marin, we started taking permutations at random, which is not perfect. Now, there are other ways of dealing with the unavailable evidence. One is bridge sampling that started in the 70s, but that was applied to a difficult Bayesian problem from the late 90s. And in particular, in Sylvia's book, there is a whole coverage of that, where using a substitute to posterior again, a la Chib, you can find an unbiased estimator of, of at least the numerator of the evidence. And you have to learn about Q while using a proposal that is inspired from the simulation and the missing latent variables. All right. Now, I mean, the difficulties with that average again is that, I mean, it's correct if we take all permutations, but at the same time it's highly inefficient, because most of these terms, once we introduce permutation, will be zero. And so with Kate Lee, we tried to improve the efficiency by removing permutations and only considering those that could provide non-zero terms. So these were the paper and an algorithm from the paper that we wrote a few years later that will reduce some of this complexity. Now, this is only one tip of the iceberg, because I mean, there are different approaches that avoid including the entire data or incorporating the data term by term. So, for instance, Nicolas Chapin has a paper following that path, where the evidence takes into account progressively the data and stabilizes on Lady. And he has a more recent paper by with Steven Buchholz in 2021, where so you keep progressing from a temperature of 0, where you simulate from the prior, all the way to 1, where the entire sample is incorporated. And well, following this sequence of steps, which is costly because you have to repeat a simulation, and therefore a Gibbs sampling or an alternative call for all the temperatures between 0 and 1, you do have a representation of the evidence by this converging proposal. Now, something that could be done about CHIPS solution is to find a CHIPS version or version of CHIPS evidence approximation that ignores the label switching difficulty. And again, this is feasible, rather surprisingly, by integrating out the parameters. So instead of using CHIPS formula opposing the data and the parameters, you can consider Chip's formula that opposes the data and the cluster allocation. So this fracture C notation is the partition of 1n based on the z. Okay. So if you consider jointly X and C under conjugacy for the various components of the mixture, you can produce a marginal density of C given the clusters, and along with the prior distribution of these clusters. And if you do that, again under the conjugacy assumption, you have both a closed form expression for the joint and a Rao-Blackwell approximation of the posterior distribution of the clusters given X. And because these clusters are invariant under permutation of the indices, there is no label switching. And then you can also follow, just to finish the comparison in the literature, that there are also solutions using sequential importance sampling, where while you use a population of particles that you follow across iterations. And well, the same principle as the previous sequential solution, that you have the same approximation to the evidence. So here are pictures of comparison of these different solutions that we run in this paper. Really, it is not very easy to read, so let me move to the next slide, where again, time of computing, we compare the different solution. This is the original chip version in terms of error, so it starts quite high. Bridge sampling, actually, it's a bit disappointing in terms of time, because it has a large error, a bit lower than chips, not that much. Regular sequential Monte Carlo that is based on particle is actually quite costly in that problem. So it doesn't also produce such great performances, while chip partition solution has better performance in terms of error, while the optimal solution in that situation for that experiment would have been the sequential importance sampling. So one of the conclusions of this paper is that actually bridge sampling, arithmetic mean, which is simply simulating from the prior and averaging, so it costs nothing, but it's quite variable. And the original chip method quickly failed to scale with the number of observations. And somehow the most reliable method, even though chips based on partition stands its ground for a while, is sequential importance sampling. Now, there is something that is even more curious in this field, which is that if you instead follow a non-parametric approach with a directly prior, Cheb and Basho have found a way to exploit Cheb's formula in that situation, again by integrating out the parameter and using only the m in the stick breaking prior as the remaining parameter. And so there is a way to write down base formula with this approximation in the ratio, which is quite amazing. And in the same paper, we compared that with Charlie Geyer's mythical reverse logistic regression approximation to the evidence based on the form of inverted logistic regression. And I found that, well, the performances of this reverse logistic regression, which is here, are quite good compared, say, with other solutions in this non-parametric Dirichlet case. Okay, I'm a bit unsure how many minutes I've left, if any. But let me finish with a few words about priors. With Clara Grazian, we tried a GFS prior, and actually you can find you can find a way to numerically implement the GFS prior based on its definition in, well, limited number of components and limited number of dimensions. Actually, but however, I mean, the problem is that we are never certain that the posterior is proper in that situation. And if you run MCMC, I mean, it's well known that MCMC is not the best tool to check or assess properness, because it has its own difficulties. And when you run, say, a Gibbs sampler with an improper prior, it may totally fail to signal that I mean, something is wrong. However, there is an alternative where we can well, not use a GFS prior, but use least possibly informative prior, which is to reparameterize, say, a location scale mixture through the global mean and the global variance, because thanks to this compact constraint on the other parameters, all parameters but global mean and global variance are part of a compact space, and therefore we can use a uniform prior on these other parameters plus well, the standard location scale non-informative prior on mu and sigma, and the main result of that paper is that I mean, the posterior is proper with two observations. So no matter what the number of components, there exists a reference prior that works out in that situation. Okay, so I've reached my last slide, and this is a picture of I took from a plane from Venezia to Paris. I wish I could have taken it today. Again, I'm sorry not to be there. Is it a dream or reality? Well, to me, it remains a bit of a dream to estimate the number of components. Of course, I'm not mentioning at all the case of clusters, namely that unless you have a very large sample size, there will remain some uncertainty about the number of components and on the dependence on the prior modeling, which is why I insisted a bit heavily on that side. While computational wise, I think we have good enough array of tools that we can trust that computation is not the issue. It's rather the inference. Thank you for your attention.
So thank you for your presentation, and you are perfectly on time. We have two discussants, Alberti and Tommaso De Gomez.
Okay, great. Can you hear me? And Christian, can you hear me as well? Okay,
yes.
Great. Well, so in the meanwhile, big thanks to the organizer for having me here. I'm very honored to discuss this talk by Professor Robert, and a big thank to the organizer for putting all this conference together. There are a lot of superstar in statistics, so I'm very happy to be here. And so to start my discussion, a few remarks. So there might be some overlapping between the discussion I'm making and some points that you have heard from others as well, also because the two talks by Professor So the previous talk and this talk, there is a bit of overlap between them. So, you know, the two components are not very well separated, we can say. Okay, so I'd like to make one, yeah, because I can say Fruish Wagner, but it's a bit difficult, and still I don't want to say Silvia because it's too friendly. So, so I'd like to start by making one step back when we talk about clustering and this kind of problem, because so very often we see these pictures in which we do have these two groups, which are very well separated, and we are like, okay, we would like a mixture model, which allows us to say, I want to have just two groups, two components, I want all the others to be set as 0. However, in practical problems, to say that we have just two groups is difficult. So just to start with a silly problem, we have real data, so some objects, and so the question is, how many clusters are there? Well, it depends. If you group observations by color, we might have 6 clusters, or we might group them by species, so we might have animals, dinosaurs, vegetables, objects, so we have 4 groups, or by, let's say, taxonomy, so whether they are alive or not, if we pretend that dinosaurs were alive, of course. And so this is just to say that clustering is per se a descriptive problem, so it's potentially very simple, but at the same time it's super, super difficult because there is no ground truth, so we don't know what is the response that we would like to get. And this has results in a lot of problems, because estimating the number of groups, estimating the number of components, how many groups are there in our data, how many groups are there in the population, these are super, super difficult questions and actually motivates a lot of research that you have heard in the past 2 talks. And so why do we want to make this problem, why we want to try to face this problem with a model? Because clearly it is very elegant, we might have uncertainty quantification. And so we know that mixture models are a model, and therefore they are wrong as any other model that we want to use. However, my point here is that mixtures tend to be more wrong than other parametric model that we use in practice. So assuming that the density comes from a mixture is not the same as telling that our errors are Gaussian, or at least they have 0 mean and finite variance. And because this is, in fact, very often we use mixtures just as a tool, and we don't think that our population is divided in 2 groups, but we use this definition just as a purely notational thing. And so what is the implication that I would like to discuss with you is that when we focus on real data, this is an aspect that we should not ignore, because we have a lot of theory, which is very rigorous and tells us, for example, we saw in Professor Robert's talk that the bias factor has some convergence property, so it is consistent. However, if you suppose that your true distribution is a mixture, or there are some cases in which the theory helps a lot, we have rigorous results, but we should interpret them with care. So, for example, what happens if the true distribution is not a mixture, which is what we might expect in practice. So we don't think that the data really, the true genetic process is really a mixture. So what happens if your model is not properly specified, or what happens if the sample size does not grow well enough? Or also another point which came to my mind yesterday is what happens if your data are not in an Euclidean space, they are on a manifold, like I talked with her yesterday. So probably you should use the theory that has been developed in that specific context. And so second point that I like to make, focusing instead on a problem in which mixtures are, so their job is a bit less difficult than clustering, which is density estimation or density regression, if you would like the density of your response to vary according to your covariates. And in that case, even when your data are structured, so even if you have some form of covariance or correlation about your observation, one thing that you can do is still attempt to estimate your density with a mixture of much simpler components, and indeed you can make your mixture as close as you want to the true density to attempt to estimate. And so this is great. This is something that we do every time. However, there are some issues. For example, when the number of variables is large, it is difficult to specify a form of dependence in very large dimensional settings. Maybe with the Gaussian is doable, so okay, just place a covariance matrix. But what happens, for example, if your data are categorical? So very often you say, okay, conditionally on cluster membership, my categorical random variable are independent. And that might be a bit restrictive in practice, because at the end of the day, if your kernels, if your single mixture component is too simple, it is true that you can characterize very well your distribution, but you end up needing a lot of components. And every time you do clustering, you don't want to have so many components. So I think that everybody would agree that a clustering that gives you 100 groups is not really the best thing that you will do. So you want to have just a few, 2, 3, 4, 5 groups that you can interpret very well. And also, there's the fact that when P is very large, most of your observation falls in the corner of your space. So, you know, you really need a ton of components there. And so some things that comes to mind to try to solve this problem a little bit, or at least an approach that we can think at when we focus as this setting is, well, one way is instead of giving to the mixture components all the work, the job to try to account the dependency on our data, can we try to move it a bit in the kernel? So can we have some components which are a bit more structured and allows us to account for some form of dependence? And in that way, I expect to have a bit more components. A part of this was discussed in the end of the previous talk. So, but what happens, for example, if the data are not Gaussian? So can we do something similar with categorical data, with ordinal multivariate data? So can we try to move a little bit of dependence there and have a structure with fewer components, which is more interpretable? And the last point that I'd like to make instead focuses more on an algorithmic point of view. And in particular, all the give sampler for mixture focuses on data augmentation, which is great. It is very elegant. And so a question that I asked myself and I discussed a lot in the past years is, so is it a curse or is it a blessing? Because it is true that data augmentation is super beautiful, gives you conditionally conjugancy, which is great. You can develop all your algorithms. The code is very, very nice. But clearly this does not come cheap, because at the end of the day, even if your model is very simple, even if your model has a very small number of parameters, you need to update and introduce an order of latent variables, a number of latent variable, which is an order of n. So at the best case, 1 per each of observation, but can be many more. So at the end of the day, you have a lot of parameters that you have to update in every cycle of your n algorithm, give sampler, em, whatever you want. And this is an issue because you are increasing a lot of your parameter space. You need to have to do many more steps. And in some cases, you are not even interested in those variables. Generally, you are in mixture model if you're interested in the clustering, but data augmentation is very popular in any not-auxentics like binary regression. And in that case, the augmented variable do not have a particular inferential interest per se. So my question is, can we try to balance a little bit of these two aspects? Because for sure, having some convenience in terms of formulas, in terms of algebraic details is great, but can we sacrifice a little bit and try to increase something in terms of scalability? This, for example, refers also to the approach for estimating the bias factor, which Professor Roberta has illustrated. And so, for example, some thoughts is it possible to try not to update all my latent variable, but only try to update a small subset, maybe just the most important one, or at least try to update them on in some way which is computationally more convenient. And I was glad to see that there is something in this direction, at least from an approximate inference point of view. For example, Daniele told us yesterday an approach in which you can approximize your posterior in such a way that the joint distribution of the latent variable is factorized in a smart way, which is much cheaper to compute. So how these things can be extended to this direction is something that I think is worth to be taken into account. And that's it, just, you know, few references and a spoiler of where we're going to be this afternoon. So big thanks to everyone for your attention and to Professor Robert for your great talk. Thank you.
Okay. Can you hear me? Not really. Okay, hope it's better. Okay, so well, thanks for staying here, and thanks, Professor Robert, for the nice talk. When preparing this talk, with this discussion at least, I had in mind, well, you know, I have this fantastic quote about tequila as a mixer that nobody has ever heard of. So here it is, and little did I know that two people before me quoted this very same point by Larry Wasserman that I think is kind of establishing a point that is a kind of a consensus that mixers are powerful tools. Everybody would like to use them because of their flexibility, because of the things that you can do with them. You can do density estimation, clustering, but at the same time, they're kind of delicate. So this slide is just for setting up the notation, which is similar to the one that we used so far. And so that was my first concern. The second one is that, you know, well, Professor Christian Robert worked on this stuff for his entire life. I'm just a young researcher. So me and Manuel were kind of worried about what to do now. So just to put the things into perspective, I downloaded some data about the paper authored by Professor Christian Robert, according to Scopus, which is more than 100. So the papers that me and Manuel read combined is about the same number. And while the list goes on, the number of co-authors by Professor Christian Robert is in the 300s, and the number of Twitter followers, which is basically the best we can do in this setting, is pretty much of the same amount. And yeah, well, I omitted the number of citation because it was depressing for myself. Anyway, let's get started. So this is a talk about estimating the number of mixer components, or the number of clusters, really, because as we learned this in the talk by Sylvia, these are two different things. So the Kn is the number of clusters, so the number of non-empty groups we have into the data. And this is kind of evident in Bayesian on parametrics. So the number of mixer components that you have in Bayesian on parametrics is infinity. And the question now is, can we learn the true number of cluster H naught? So suppose that the data are generated according to a mixer model, and this mixer model has a fixed amount of components, H naught. Can we learn something, either using a finite mixer of finite mixer, an overfitted mixer, or a Bayesian parametric model? So here there is a biased list of references. So this is not comprehensive. This is just a list of papers that I've read. So the first one is a kind of a well-known paper now that has been cited several times by Judith, who is here, about overfitted mixers. So it's suppose you have a mixer model with more components than the actual number, H naught. So can we recover the true true number of components, at least asymptotically? So that's a positive result. And in the literature, then there is this paper by Miller and Harrison which is a negative result then. So it's a bad result because it says that if you use a Bayesian or parametric model for estimating the number of mixer components, then you get an inconsistency in the sense that the posterior distribution does not concentrate to the true number with probability 1. So but then there is another paper by Ascolani, Antonio Lioi, Giovanni Rebaudo, and Giacomo Zanella, which is going to appear in Biometrica, which is kind of saying the opposite in a slightly different situation. So you still use the Dirichlet process mixer models, but then you place a prior on the concentration parameter. And in those cases, you kind of get again consistency in the number of mixer components, which is kind of intuitive, but you know, it's a difficult game. So the point that I want to make here is that estimating the number of mixer components is a delicate problem. So it really depends on a lot of stuff. And also there are a lot of things that are going on here, including the identifiability issues, the fact that the penalty you may want the penalty to depend on the sample size as well. So it's a delicate game, but under a lot of assumptions, and in particular the fact that the kernel is well specified, you can do something here. So now that there is another problem though. So these are data, these are artificial data that I generated. There are clearly two clusters. This is a mixer model because I generated this data. And as you can see, the data are not Gaussian. So this is not a mixer of Gaussian, it's a mixer of something else. And if the kernel is misspecified, so if I use a Gaussian mixer models, what I get is this picture here. So the number of mixer components that we're estimating is wrong. And what you typically get is you overestimate the number of clusters. So this is kind of expected, but it's something that you actually encounter a lot in practical situations. So this is a practical problem. So the theory, it's kind of obviously saying that you shouldn't do that, but in practice, how do you do? I mean, you don't know the kernel in advance, so you need to do something about it. So, okay, so before moving on, this is a remark. So even when you are in this kind of situation, even if you use a Gaussian mixture of Gaussian distribution together with a non-parametric prior, for example, one thing is doing clustering, another thing is doing density estimation. So density estimation is an entirely different problem, and we should not use the same. We should not treat them as if they were exactly the same thing. I mean, a mixture of Gaussian distribution could recover the true density, irrespectively of the fact that it's not a mixture of Gaussian. Of course, you're going to need more mixture components to approximate that unknown density, but that's something that you can do. And this is a reference that says that. But if you're interested in clustering, which is often the case, so what can we do? Well, see if the multivariate Gaussian is not ideal, what about coming up with different kernels, more flexible kernels? Well, in principle, that's a good idea. So for example, you could use multivariate skew normals. Of course, there is the issue of getting, I mean, there are computational issues related to that. Skew normals might be a little bit more demanding on computation, but still. So this kind of mitigate the problem, but it's not entirely solving it. I mean, if the Gaussian is sometimes misspecified, maybe the skew normal is again misspecified in other setting and so on and so forth. So it looks like an unsolvable problem. So another thing that somebody could say, well, let us try non-parametric kernels. So non-parametric mixture of non-parametric stuff, which looks like a nice idea, but then you have a lot of identifiability issues that are kind of that are addressed in this paper by Sylvian again and co-authors. And the first two papers instead are kind of going into the other direction. So they're pushing the direction of providing new kernels. So the first one, for example, is nice. Is proposing a kernel with a curvature essentially. So this is this Fisher Gaussian kernel. So the second one is a paper by Bruno and David Danson about enriching mixture models. So you have a kind of mixture specification for the kernel itself, on functional data. So these are the two possibilities that comes to mind, at least to me. And so one thing that I would like to understand now is that, well, in this mixture setting, can we get something, some theoretical support, like as an asymptotic statement saying that maybe we can get the correct number of mixture components using this non-parametric kernel situation? Is it that too ambitious, or is it something that is possible? And yeah, so that's a difficult question maybe, but it's something that I would really love to understand better. So the final slide that I have is, well, let us forget this mixture setting entirely. Let us try to move on with something more exotic, if you want. So let us try to abandon the usual Bayesian paradigm, and let us move on with this setting called Gibbs posterior, which is a setting that has been proposed by Bisseri and co-authors in a JSSP paper. So which basically says, well, instead of a likelihood function, let us try to use this loss function. So you consider a generic loss function, and you take the negative exponential of that loss function, you attach a prior, and you treat what you get as a genuine posterior. So of course you have a lot of additional flexibility in doing that, because you're enlarging the modeling possibility in a sense. On the other hand, you have a lot of other difficulties, namely the fact that the loss is defined up to a multiplicative constant. So that's the first issue. The second issue is, well, it's not a probabilistic model, so you do not have really a generative process. I mean, it's something to that is nice to play. So that's what we did, for example, with Amy and David. The point here is that, so if you abandon the usual probabilistic setting, even the definition of the cluster itself can change. So one thing that was touched by Emanuele was there are different definitions of clusters. And so one thing is saying that clusters are the one defined by mixture models, and that's one thing. And so we can certainly try to estimate the number of mixture components, assuming that the model is that. But there is another perspective that I like a lot, which is, well, suppose the data are generated according to whatsoever mechanism. And so we just want to partition them, irrespectively of the fact that there might be or not a mixture model, which is a sensible question. So this is what private companies are asking. So suppose that you get from your nice mixture model, which is consistently estimated number of mixture components, and suppose that the true number of components is 200. So what do you do then? So do you give 200 mixture components or cluster to the expert? Sometimes you cannot. So maybe they ask you specifically for 4 cluster because that's what they want to do. So abandoning the usual probabilistic setting allows you to fix this H, so the number of clusters that you want, in a kind of a subjective manner. So it's basically the resolution at which you want to analyze the data rather than something that you learn from the data itself, which is a kind of shift in perspective. It's a different philosophical viewpoint, but still there is a lot of uncertainty in that, and a lot of it can be said even in an asymptotic sense. And with this, I'm done.
So we have time for additional questions from the audience. Do you have any?
Yeah, okay. Thanks for everyone for talks and things like that. Because the two talks are very similar, would it be possible to have like a discussion on both talks on the problem of clustering and estimating the number of components? Because the discussions they were super interesting, but it's all about like the robustness story, and it's a difficult question for me, because as was said, as soon as you don't put a model, then the question of robustness on the number of clusters and the identifiability of the clusters makes no sense anymore, because what's a cluster? And then people can draw potatoes and they're right. Nobody can say they're wrong because they haven't defined what a cluster is. The cluster is defined by the model. And so for me, it's always something a bit delicate. But I really liked the idea of this sort of, like if you fix yourself up, okay, my cluster is this, and then I want to find the best partition that will correspond to, that's a different story in a sense for me. But you can't be robust. I mean, because you've defined what you wanted to do and there is no robustness there for me. And at least I don't know. And so I would be interested in hearing what people think, like everyone think on this subject of what a cluster is and how do you do robustness. So there is this identifiability theorem that says that if you have 3 conditional independence given the states, observations, then you can identify everything. You can be totally non-parametric on the emission distributions. You can identify the number of components. And so you can have everything for free, but you need a bit of structure. So it's just a structuring assumption in here. And you have the same with a hidden Markov model. So you don't, everything is identifiable. And so I was wondering whether this is something you can try to think about. Like for instance, the mixture of, sorry, I'm speaking too long, but so the Sylvia's idea of these non-parametric mixtures of mixtures. So Sylvia, are you having this sort of diagonal covariance matrix in your non-parametric, in which case maybe you've got this non-parametric conditional independence of your observations, because in which case then you'd be identifiable.
Any additional question?
Maybe out of context, but since Larry Wasserman was mentioned, and his suggestion was to avoid mixture at all, but I think there is a work by Larry Wasserman called Universal Inference, where he tries to get a lower bound on the number of components, assuming of course a mixture model. So I was wondering, this is my answer to the title of the discussion. You don't follow the previous story, so I would like to know if you are familiar with this work. It's by Aditya Ramdas and Larry Wasserman, 2019.
Please brief.
Just a remark, in my webpage, I posted data from 10,000 galaxies. So if you want to try, you know, instead of 82 galaxies, try that.
So you have, Christian, you have a few minutes to answer. Please.
Yeah, thanks. Sorry. And so, first, I completely agree with Judith that the main question on estimating of components or number of clusters is very evil in the Larry sense, in the sense that, yeah, if you must define what's a cluster before proceeding further. And so, I mean, to relate with the discussions, I really like this Gibbs generalized prior idea, in that you first set what you mean by a prior before proceeding with the estimation, because either you believe in the mixture all the way to the end. So I mean, there's no debate that the data doesn't come from this mixture, but that's a very religious belief that is not correct, or you don't, and then inevitably, as the data increases, it's I mean, the data is misspecified, and therefore estimating the number of components or number of clusters is not reflecting on the data, but is a consequence of this misspecified model. So it's not going to work. Well, if instead what people want in clustering is set clearly from the start, and again, that's why I really like the reframing in terms of through a loss function or discrepancy function. If it's set from the start, and then you can start hoping for consistency. Now, another point was made during the discussion that was interesting, is this idea that of an increased dependence between the data points could proceed further and amalgamating them into clusters, but somehow this means, once again, changing the model so that data staying together in a cluster would have a stronger constraint than just being a result of an IID model. So I think that's the main thing I want to answer from this point.
Thank you so much for your talk. And so